One of the design types is using the randomized block design. This is useful if you think that there's something wrong with a possible experiment. Say you're running a clinical trial in a hospital where you've got 500 patients and you're giving them maybe half of them a placebo and half of them some sort of medication to lower their blood pressure, and you get some really strange results. You can run the exact same experiment at a number of other hospitals to try to determine if there's something wrong with the drug, it didn't work or worked too well or something along those lines, or if you've got a significant difference at the location. So say the original place you tested at, they made tons of mistakes and they have sloppy procedures and so forth. That would come out in randomized block design. You could test to determine if all of the different locations were the same. So the basics of the ANOVA, there's the basic ANOVA tables down here. So we have the treatment means, which will come out to be the same thing. However many different categories we have, that's what we're going to test. Our block design, however, is going to test each individual location, or in our example here, it's going to be a different golfer. So this experiment has, instead of using a mechanical arm to hit balls, I guess, uniformly or in the hopes uniformly, we have here 10 different golfers, each getting one golf ball from each of the 4 brands. So we're going to determine if A, there's a uniformly good brand again, and B, if we're having issues as far as different golfers hitting it. Now, anybody who's golfed will realize that even professionals, if they hit a driver, probably won't be hitting it the same distance, especially if we get 10 of them. So we're probably going to have some sort of block design or block differences as far as that goes. So this is the basics of it. If you want to test for treatment, you're going to use this F using the numerator degrees of freedom of k minus 1, and these are the error degrees of freedom. And if you are testing for the block, basically testing for a difference in this case, the different golfers, we're going to have 10 different golfers, so 10 minus 1 will be 9 degrees of freedom will be our numerator, and we still use the error. We're still taking the mean square of this row, in this case the mean square for block, we're dividing it by mean square error. You always divide by the mean square error to get your F values, your test statistics. So our treatments, we have a p-value of 0, or at least 0 to 3 decimal points, so we're going to reject there. In similar instance what we did before, we're going to have brands hitting it basically a different distance. Now, we also have tested to determine if there's a difference in golfers, and that too shows a p-value of about 0. We use the second one for that, and they could be different numbers. We didn't have to get the same p-value necessarily, and again, they're not the same p-value. They're different. They're just different. A few more decimal points down, probably something along those lines. So in this example, we reject, indicating that we have a difference in at least one treatment mean. So at least one of the brands goes in a different distance than the others, or than at least one other one. And we have a difference in the amount of golfers, or in the distance that the golfers hit all their balls uniformly. And this is kind of how you use a block design. Again, make sure that you use the p-value from the given row when dealing with the golfer, but this test runs pretty much the same as our treatments.